Hi, it's Kate, and this is the second video for week 6 of Math 23B. So we have these abstract vector spaces. Let's let V be a particular abstract vector space of functions. Then when we have an evaluation rule like plug in 1 for x, is a linear transformation, actually, that goes from this abstract vector space to the real numbers. It uses the rule that it selects a particular function in that abstract vector space and it returns that function's value at x equals 1. What's critical about this is we can actually use these mappings, these transformations that are evaluation rules on these abstract vector spaces to see how we can revisit integration rules. We only have a couple at our fingertips right now. We discussed Simpson's rule, and really what Simpson's rule is a weighted average of various values for this function L, which is plugging in different x values for functions, in order to approximate the value of their integral on a particular interval. So here we have Simpson's rule written out using this particular notation. Now we're going to look at other types of rules that are more and more accurate on various spaces, abstract vector spaces, and these are quite interesting to take a look at. Note that an integration rule is a linear transformation which goes from the abstract vector space of functions and it spits out a real number. Now, what it acts on is one of the functions in the vector space, and then the real number is actually the integral of that function from -1 to +1. Now, if V, that abstract vector space, is the four-dimensional space of polynomials of degree 3 or less, then this rule of approximating the value of that function's integral, Simpson's rule, is actually equal to the value of the function's integral on whatever interval you're looking at, and this was actually part of the quiz that you just took. And this is easily proved by evaluating both this function s as well as this function r, the Simpson's rule approximation as well as the rule for integrating these functions on the basis for this abstract vector space. Now, of course, for cubic functions, the components, the elements of the basis, are 1, x, x squared, and x cubed. Now, the restriction to the interval -1 to +1 is not a serious one. Consider t. It's the linear transformation which maps -1 to a and +1 to b. So we can use t to parameterize our interval from a to b. You can actually prove that Simpson's rule is exact for cubic polynomials on any interval a to b. It doesn't have to be -1 to +1. And so what's cool about this is that we can generalize this idea. By a clever choice of basis, we can invent Gaussian integration rules that are exact for polynomials up to a certain degree on this interval from -1 to +1. And the simplest of these rules is this particular weighting. Note that the notation up here is saying that L1f means I'm going to take the function f and evaluate it at the input 1. So here we are equally weighting f evaluated at -1/√3 and +1/√3. And you'll see already in your version you'll find an f right here and right here. I'll write that in right now. And the proof is very similar, right? We compare the output that we get from this Gaussian integration approximation with the actual value for the integral on the basis, each element of the basis of the particular vector space. So what's cool is that the same linear transformation t as was used for Simpson's rule extends these Gaussian rules to an arbitrary interval. It doesn't necessarily have to be -1 to +1. So this is a way to use the bases of these abstract vector spaces to prove integration rules and approximation methods that are exact on an entire space of polynomials or particular functions by looking at the elements of the basis and showing that the rule holds for every single element. And knowing that integration is linear is a huge help in the proof there, because if this holds for every single element in the basis, then it's going to hold for any linear combination of elements of that basis, which is the entire abstract vector space. Another interesting characteristic of abstract vector spaces are inner product spaces. And the inner product is a real number on an abstract vector space. It is written like this notationally, and it is subject to the following axioms, which is that it's linear in the first factor. Note that if you are able to factor out a coefficient on one of the two main components in the inner product, then the overall effect is to take that inner product and multiply it by that scalar multiple. So for instance, C1 times V1 plus C2 times V2, take that inner product with W. That's the equivalent of taking C1 times the inner product of V1 and W plus C2 times the inner product of V2 and W. So this is generalizing the distributive law for the dot product. The inner product is also symmetric, so the order of taking the elements of the inner product is not important. And it's also positive definite, which means that if you take the inner product of a vector with itself, an abstract vector with itself, it's going to be positive or equal to 0, and it's going to be equal to 0 if and only if the abstract vector is equal to the 0 vector. So what's great is that the space here of Riemann integrable functions with inner product defined accordingly. Let's take a look at this. This is how we define the inner product of two functions. Riemann integrable functions, the inner product of f and g is going to be equal to the integral from -1 to 1 of f times g. Now with this inner product, the Gram-Schmidt process can be used to create a basis of orthogonal polynomials on an abstract vector space of polynomials. So what's interesting about this is that you can build bases for the space that have no quote-unquote shared component, just like the Gram-Schmidt process created when we were dealing with simple vectors that existed in Rn. Given a first basis vector and any second vector that is independent of it, we can construct a new basis vector to that first one that's orthogonal to it by the following rule. Basically subtracting off the component in that second basis vector that is common to the first. So you're able to build orthogonal polynomials and construct new bases for the space that behave in particular ways, so that each element of the basis has a 0 inner product with the other. You can see concepts like this come up in the future if you're ever studying things like Fourier series. Another application of a change of basis is something called polynomial interpolation. Note that the old basis consists of monomials like 1x squared, and each new basis vector is a polynomial that equals 1 at one of 3 chosen evaluation points and 0 at the other 2. For example, if the evaluation points are 1, 2, and 4, we check out this polynomial that equals 0 at 1 and 2, and then is equal to 1 at 4. And in this case, it's really easy to write down any column of P inverse. What we're going to do is we're just going to evaluate each of these basis elements at 1, 2, and 4. And what P can then do is find an interpolation equation. That is, for any quadratic polynomial, it can express the function value at 3 as a linear combination of the function values at 1, 2, and 4. Alternatively, it can take requested function values, say, okay, I want a polynomial that's equal to this at 1 and this at 2 and this at 4, and it could churn out the necessary coefficients on 1x and x squared to give you a polynomial that does that. And we're going to do several examples in class this week. Another interesting application is Fourier analysis. The old basis consists of functions like 1 cosine squared and cosine to the 4th x, and the new basis consists of functions like 1 cosine 2x and cosine 4x. And using various identities like this, we can write new basis vectors in terms of the old and construct change of basis matrices. And then we can invert them as well, expressing old basis vectors in terms of new basis vectors, basically moving back and forth between the two bases. We'll be doing examples of this additionally. Partial fractions, we can also look at how these are old basis vectors, these are new basis vectors, and it only takes a little bit of algebra to find the linear combination to express one set in terms of the other. You can then write down one change of basis matrix and invert it to get its complement. In this case, it's a little bit easier to write down P, and then P inverse does a partial fraction expansion. Now, this is a little bit sort of abstract given that we don't have any examples quite yet, but you'll be doing tons of examples this week. The most important thing to remember are the two pieces that you need to be clear with which basis you're working in. We've left the standard basis behind. We are currently talking about abstract vector spaces. So what are the elements of your basis? And furthermore, when you're looking at a particular vector that has something like this in it, A, B, and C, remember that A is the coefficient on the first element of the basis, B is the coefficient on the second element of the basis, and C is the coefficient on the third element of the basis. And it's that linear combination with these coefficients encoded into this vector as its components that describe the element of the vector space you're dealing with. That's the most important thing to remember because it allows you to keep clear in your mind which vector space you're in, what particular vectors mean, and also whether or not you need to invert something to map from a given space to another. So that's my advice to you as you move into some of the examples that we'll be seeing this week. The idea is to take the nice, hard, concrete examples of vectors and apply them into this new, more abstract space. No longer do vectors necessarily make sense as far as arrows or increments of change, but we're using the various mechanisms at work in linear algebra to represent similar mechanisms in these new abstract vector spaces. It's a very rewarding week, lots of material to cover, and of course email if you have any questions.